Hello once again, class, and welcome to another mock lecture. Today we're going to be tackling double angle identities. Let's get to it. First, we're going to start by deriving the double angle identity formulas, and actually they come from just looking at angle sum identities. We're going to start off by looking at sine, and it's actually kind of an interesting algebra. I don't even know if trig is really the right word. It's more like a property of algebra, but maybe an unexpected one. We're going to start off by saying that the sine of 2 theta can be rewritten as the sine of theta plus theta. And if you were to combine like terms here, you would just get 2 theta. Now the reason that this is useful is because we know the angle sum identity for sine, and at this point, that's really what we're doing, right? The angle sum identity for sine says the sine of alpha plus beta is equal to the sine of alpha cosine beta plus the cosine alpha sine beta. But alpha and beta in this case are both theta. So when I go and I write out the angle sum identity using these two things as the input, theta will go in all of these positions, right? Because alpha and beta in this case are both theta. So we get this. Combining like terms again, right, because sine times cosine is really the same as cosine times sine. You just have to use the commutativity property of sine and of multiplication. And then you flip these two things, so you're getting something plus itself, which means that you have two of them, and that is the double angle identity for sine. The sine of 2 theta is equal to 2 sine theta cosine theta. To derive the other two, we'll start with tangent. You're doing the same thing, right? The same trick applies. You're going to turn 2 theta into theta plus theta so that you can use a sum identity. In this case for tangent, so you get tangent theta plus tangent theta. That's 2 tangent theta in the numerator, divided by 1 minus tangent theta, which is tangent squared theta in the denominator. Okay, so we can add that one to the list. Now it's a little bit of a different case for cosine. We start off the same, turning 2 theta into theta plus theta. The cosine of theta plus theta will give us cosine squared theta minus sine squared theta after you use the sum identity for cosine. Now the thing is, this is one version of the double angle identity for cosine, because one of the things that's interesting about this particular formula that's a little bit different than the other two, although you could probably do this with tangent, but I think it's less useful, is that we have identities that can turn cosine squared theta and sine squared theta into each other, essentially. For example, if I take cosine squared theta, I can actually turn that into 1 minus sine squared theta. So now cosine 2 theta, the double angle identity for cosine, can only involve sine. You can write it in such a way where if you're only given sine, then you can use this version, right, of the double angle identity. 1 minus 2 sine squared theta is the same thing, right, as this. It's the same identity. It's just written in a different way. Similarly, you could take sine squared theta and rewrite it as 1 minus cosine squared theta. Doing this, after distributing the negative sign to 1 minus cosine squared theta, you can combine the cosine squared thetas, and there's a third version, right, for the cosine of 2 theta. The double angle identity for cosine can be rewritten in 3 different ways. You have 3 options, basically, which is nice. So now we need to add these identities to our list of current identities.
Bruh.
Okay, well, you know what we're going to do? We're going to get rid of the I'm sorry definitions. It's time to go. You've served your purpose, and I'm going to take you off the list of current identities just so that we can have the main ones on here. That's a little better. All right, so here's all of our identities, minus the definitions. Let's get to some examples using the double angle identities. All right, example number 1. Suppose cosine theta is equal to negative 12 over 13 and sine theta is greater than 0. Now, by the way, so this setup is something that we've seen before. Like normally after this, it's like, okay, now find the sine of theta, find the tangent of theta, find the cotangent of theta, right? Find the secant, find the cosecant. But now what we're going to do is we're going to find cosine 2 theta, sine 2 theta, and the tangent of 2 theta. We're going to find the double angles of theta for the 3 basic trig functions. Well, the setup is still the same. You have to figure out what quadrant you're in, right? And in this case, since we know cosine is negative and sine is positive, we have to be in quadrant 2. That's the only location where that happens. So when we draw our right triangle, we're looking at something like this, right? Cosine theta is given. That's adjacent over hypotenuse. So we got negative 12 as the longer kind of base of the right triangle in quadrant 2. 13 is the hypotenuse. Sine is going to be positive, and if you use the Pythagorean theorem to figure out what that missing side length is, you get 5, because 5, 12, and 13 is a Pythagorean triple, which is cool to know. Okay, now we have all the information that we need to find cosine 2 theta, sine 2 theta, and tangent 2 theta, because now that we've filled out the triangle, we know the sine of theta is 5/13. So let's go ahead and start off with cosine of 2 theta, which, by the way, this is the one that we have options for. And in fact, I could have actually found this without even finding sine if I wanted to, because we could write it as 2 cosine squared theta minus 1. And cosine theta was given, right? So again, that's the really cool thing about the double angle identity for cosine, is that you have options. Maybe you're only given sine, well then use cosine 2 theta is equal to 1 minus 2 sine squared theta. Maybe you're given both of them, right? In which case, maybe you want to use cosine squared theta minus sine squared theta. Or maybe you're only given cosine. You know, maybe I wanted to find the double angle identity for cosine before even thinking about what quadrant I'm in, or what sine is supposed to be. I could then use this version. Since I couldn't decide which one to go with, I just did them all. We get this. We get 119 over 169 is the solution. No matter which of these that you choose, you're going to get the same answer, which of course makes sense. Otherwise, the double angle identities wouldn't be equivalent, right? But they, because we always get the same thing, that's why we're able to choose, which cosine double angle identity to go with. Okay, sine is more restrictive. There's only one double angle identity for sine. The sine of 2 theta is equal to 2 sine theta cosine theta. So I'm just going to plug in what is cosine theta, which is 5/13. Nope, that's sine theta, 5/13. I'm going to plug in cosine theta, which is negative 12/13, and then I'm going to multiply all that stuff by 2. In the denominator, you get 13 squared, which is 169. In the numerator, you get 5 times negative 12. That's negative 60 times 2 is negative 120. So negative 120 over 169 is the sine of 2 theta. Okay, and that finally leaves tangent for us. The tangent of 2 theta you could use the double angle identity for, but I don't really think that you should. I mean, it's up to you. If you want to use the double angle identity, that is your decision. That's your choice to make. For me, though, we've already found the sine and cosine, right? We found the sine of 2 theta and we found the cosine of 2 theta. Tangent of 2 theta is just sine 2 theta divided by cosine 2 theta by a reciprocal identity. So I'm just going to do that, right? And then I'm just going to plug in the values that we know those things are. So sine of 2 theta is negative 120 over 169. Cosine 2 theta is 119 over 169. This is looking like kind of a weird fraction, so I'm going to rewrite it like this, which means I got to flip and multiply that second one, so we get negative 120 over 119, and we are done. So first example here, more of a kind of a calculation. And double angle identities are useful kind of across the board. I tried to do an example of each use in problems. By the way, before we move on, I wanted to discuss, oftentimes you might be asked, okay, what quadrant is 2 theta in, right? We know theta is in quadrant 2, but what quadrant is 2 theta in? If we double the angle, what quadrant are we lying in? Well, to figure that out, look at what we got for sine and for cosine of 2 theta specifically. The cosine of the double angle, right? The cosine of twice the angle is a positive number. We got 119 over 169. The sine, right, of the double angle is negative. It's negative 120 over 169. So what quadrant is cosine positive in and sine negative? Well, the only quadrant that's the case for is quadrant 4. So then we know 2 theta is in quadrant 4. It's possible that 2 theta could be in quadrant 3, right? Maybe the angle is only like 2 pi over 3, right? Then double the angle would be 4 pi over 3, right? That's in quadrant 3. So it really depends, how far into quadrant 2 we are. That determines what quadrant the double angle is going to be in. Okay, anyway, moving on. Okay, example number 2. We're going to evaluate the cosine of 2 sine inverse of 1/3. Now, I put this one in because I think initially when you look at this, it could be kind of confusing and what it is you're supposed to do. Eventually, we're going to get some kind of cosine output. So we're going to get some x coordinate on the unit circle. And so to start this, I would say that the sine inverse of 1/3 is equal to theta. Let's just call that a theta measurement. And then we can use properties of inverses to say, okay, well then the sine of theta is equal to 1/3. So ultimately, we've turned this problem into just a double angle for cosine of 2 theta. Because we know theta is sine inverse of 1/3, that's going to be replaced with theta when we rewrite cosine of 2 sine inverse of 1/3. So now I'm just going to use the double angle identity for cosine. All right, and that's going to give us 1 minus 2 sine squared theta. Now you might be wondering, Mark, why are you using 1 minus 2 sine squared theta? Well, that's because the only trig function I know is sine theta, right? We don't know cosine theta. We don't know any other trig. I mean, I guess that's the only other one you would need to know to use a different version of cosine 2 theta. The point is, since we only know sine of theta, then I want to use the 1 minus 2 sine squared theta variant of the double angle identity for cosine. Okay? Because we know the sine of theta is 1/3, we can just plug in 1/3 squared for the sine squared of theta. So then we get 1 minus 2 times 1/9, which is 2/9, and then 1 minus 2/9 is negative 7/9. And we're done. Very quick calculation, right, for that one. Okay, now let's get into the good stuff, right? We're going to do some proofs. Prove the double angle identity for secant is secant squared theta divided by 1 minus tangent squared theta. Now I'm going to do this, but I'm not going to add it to our main kind of list of identities. Arguably I should, but I don't want to have to record all the double angle identities for all 6 trig functions. Knowing the base 3 are enough to figure out the other 3 anyway. But yeah, this is the double angle identity for the secant. Secant of 2 theta is in fact equal to secant squared theta over 1 minus tangent squared theta. Let me prove it to you. Okay, so first we're going to claim that this is the case. Right, that's what we're trying to prove. And I'm going to start with the left-hand side. So secant squared theta over 1 minus tangent squared theta. First order of business is I want to get everything in terms of sine and cosine, basically. So I'm going to move the secant squared theta to the denominator as a cosine squared theta, and that's just by a reciprocal identity for secant. Then I'm going to distribute that cosine squared theta in the denominator. So I've got 1 over cosine squared theta minus cosine squared theta tangent squared theta. Now tangent squared theta, this thing, is sine squared theta over cosine squared theta. And if we're multiplying it by cosine squared theta, then what happens is the cosines cancel, and you're just going to be left with a sine squared theta there. Now, but the denominator at this point is the double angle identity for cosine 2 theta. Right? Cosine squared theta minus sine squared theta is one of the 3 variants for the double angle identity for cosine. So I'm just going to say this is by a double angle identity for cosine. We now have 1 over cosine 2 theta. It's in the denominator though, and the reciprocal of that is secant. So then we get secant 2 theta. So we started here, we ended here, therefore that thing's got to be true, and we're done. Okay, so if you wanted to, you could add it to your personal list of the double angle identities. This is true. And you could certainly quote it for anything that we do after this. You can say, oh, this is by the secant of 2 theta, identity that Mock proved in a video. That's totally fine. You can do that. All right, so let's move on to the last example. Now, the last example that I wanted to cover is an equation. So this is a pretty basic one, but I just wanted to show you there are some pretty cool things you can do with double angle identities to help you solve equations. For example, this one says the cosine of theta minus the sine of 2 theta is equal to 0. We want to solve this for all theta, which means we're going to have to do the plus 2 pi n or the plus pi n or whatever it is that we end up getting. Typically, when I solve these things, I want to look for factoring. I want to try to factor some stuff. Obviously, since we're using 2 different trig functions here, there's really nothing to factor right now. But if I use or instantiate a double angle identity for sine, then we would turn this into cosine theta minus 2 sine theta cosine theta, for which there's a cosine theta in each term. So I can actually factor that thing out of there. And it'll become cosine theta times 1 minus 2 sine theta. Now, this is good. Now, so let's back up. Why was I wanting to factor in the first place? Well, the equation's equal to 0. Right, and whenever I see that an equation's equal to 0, I'm thinking, okay, well, if I can factor, then we can turn this into some kind of 0 factor property situation. I did factor. Since we have something times something else is equal to 0, then we can set each of them equal to 0 and solve them individually. That's the 0 factor property. So that's kind of my mindset. When I see an equation's equal to 0, I typically think, oh, if I can factor, then I can figure out the solutions for something that's maybe only using a single trig function in this case. We're trying to solve cosine theta is equal to 0. Let's tackle that one first. The cosine function gives you 0 whenever you're coincident with the y-axis, which is at pi over 2 and 3 pi over 2. Now, this is one of those rare situations where you can actually get away with doing a plus pi n, even if we're using the cosine function, because pi over 2, which is the first solution, and 3 pi over 2, which will be the second solution, are exactly pi distance apart. That's really the only time that that happens on the unit circle for cosine, or for sine, it could happen if it's on the x-axis. You can get away with just using a pi n. Okay, so our first generating solution that'll generate a set of solutions is pi over 2 plus pi n, and we're done with that equation. So we turn our attention to 1 minus 2 sine theta. Getting sine theta by itself gives you that sine of theta is equal to negative a half. Now at this point, probably what I should have done is looked at reference angle stuff. So I should have said something like the sine of theta sub r is equal to the absolute value of a half, realizing that my answer is going to be in quadrant 3 and 4 because we're looking for negative stuff here. Solving this gives you theta sub r, whether you're going to take the sine inverse of both sides or just think about the unit circle, you're going to get pi over 6. Right, pi over 6 is the angle that spits out a 1/2 as the y-coordinate. So then my answer is going to be the pi over 6 equivalent in quadrant 3 and the pi over 6 equivalent in quadrant 4, such that these reference angles are pi over 6. So this one here would be 7 pi over 6, and this one here would be 11 pi over 6. So I get 7 pi over 6 plus pi over 2, and 11 pi over 6 plus pi over 2. I did not do that. Instead, what I did is I just thought about when sine theta would give you negative 1/2 on the unit circle, which of course are at 7 pi over 6 and 11 pi over 6. But then realizing that we're not working on a specific interval, so then everything that's coterminal with those things would also be a solution. So I added the plus 2 pi n. Okay, so those are some quick applications of double angle identities. Hopefully you guys learned something. If you have any questions, just drop them in the comment section below. Thanks a ton for watching, and I'll see you in the next one.